So that is our phi r. Now, suppose this y equal to phi r is a solution of our homogeneous equation. We will have 0 equal L phi r. L phi r is that is our y, x square y equal to phi r. So x square y double prime plus the term involving y prime and the y term. And then using our previous computation of the xpxy prime and x square qxy, using this computation, using this result, we will get so x square y double prime is this series. For the computation of y double prime, the power of x is r plus n minus 2, but we have an x square multiplied in front of y double prime. Do you want to see y double prime? Y double prime is here. So y double prime here. The power of y, the power of x in the expansion of y double prime is x r plus n minus 2. Okay, so our y double prime is r plus n minus 2, then plus 2. So the power is r plus n, and the coefficient is r plus n minus 1, and an. So this is x square y double prime. And then substituting the y prime term we compute in the last page. Last page is this page. So this is the computation of y prime term, which is this series. Okay, so we copy this series in our computation. So this is n from 0 to infinity, xn plus r, a j r plus j pi, where I plus j equal to n, summing over all ij, satisfying I plus j equal to n. Okay, this is the y prime term. And then the y term we also compute in the last page, which is n from 0 to infinity, ajqi. Okay, so how to simplify this computation? We just write the second order term, combine the coefficient of the second order term, which is but we also how to say, we write the order term n equal to 0 and n equal to 1 separately, and then starting the other term, sorry, we only write out the term involve n equal to 0. For n equal to 0, the first series is a0, r, and r minus 1. So this is why this is the where our r minus 1 coming. This part of the coefficient of a0 comes from the first series for n equal to 0. Okay, that is r minus 1. For the second series, when n equal to 0, the coefficient here, I plus j equal to n. So both I and j are all 0. So correspondingly, this term is p0, a0, and r. Okay, because I and j are 0, so p0, a0, and r. So a0 is move outside the coefficient. Therefore, what remains is p0r. Okay. Similarly, for the last series, when n equal to 0, that is I plus j is 0. So both I and j are 0. Therefore, a0 out and only q0 remains. So the sum of these two series, in the sum of these two series, the coefficient of xr is a0 multiplying this function of r. This function denoted by capital Fr is the integral equation if we let Fr equal to 0. So this is the exponent r should be satisfied. The exponent of we want to find solution of the form of phi r, that is xr multiplied power series. The r must make this capital Fr 0. Okay, so this is the coefficient of xr. Okay, that corresponding to the n equal to 0 in the sum of these two series. Now what the other term is n from 1 to infinity, and the coefficient is computed as follow. So this is the coefficient of r plus n in the first series, r plus n minus 1, then an. And for the second series, it is the coefficient of xn plus r is summation over all ij, which I plus j equal to n, aj r plus j q pi. That is the coefficient of xn plus r in the second summation. But we can let j I plus j is n, so I is n minus j, I equal n minus j. So we can let j, this sum is precisely the sum for j from 0 to n. Then aj r plus j pi, pi is pn minus j. So this sum is precisely the coefficient of xn plus r in the second summation. We can rewrite this sum I plus j equal to n to j equal to 0 to n. Okay, so this is the second coefficient. Similarly, for the last coefficient, we can also write it as j from 0 to n, aj qn minus j. So this is the coefficient of xr plus n for the sum of the summation, the three summation. Okay, but because the term corresponding to n equal to 0 we have written out separately, so the summation here is from n from 1 to infinity. Now we simplify this coefficient. The first, the coefficient of xr is a0 capital Fr, because this function is what we call capital Fr. And then the sum here we can take the term corresponding to j equal to n out from the summation. From these two summation, we take the term corresponding to j equal to n out, and therefore the sum becomes j from 0 to n minus 1. Because the term j equal to n will have been taken out, but the term corresponding to j equal to n can be combined with the previous coefficient to give us capital F r plus n. So in this two sum, when j equal to n, the aj is an, so we can take the aj out and compute what remains. The remaining is r plus n minus 1, and then r plus n p0 plus q0. That is precisely capital F r plus n. Okay, so this is this summation. From this step to this step, we take the term corresponding to j equal to n out, and then combine that with the previous term here. Okay, because every term we consider the involving an an, you move the an, collect the an out, and factoring the an out, and combine what remains. That is precisely capital F r plus n. For this is the r plus n minus 1, and then this is r plus n p0, and this is q0. So you can see that the coefficient of an is precisely capital F r plus n. So and this also explained that this summation is from 0 to n minus 1 for j. Okay, so this is our computation of our L phi r. If phi r is a solution of the equation, so L phi r should be 0. Therefore, all the coefficients in the right hand side of this computation should be 0. Because a0, of course, we consider a0 not 0. Okay, for a0, because we're considering what we considered is a homogeneous equation. For homogeneous equation, any multiplication of solutions is a solution. So we can assume that A0 is not 0. Okay, if A0 is 0, you replace the A. This is equivalent to raise the R to R plus 1 because there is no A0 term. So this is from X to the 1. You move the X out. That is X R plus 1 sigma, and from 1 to infinity, A1 X plus A2. A1 plus A2 X. So just the shift of the exponent. So without loss of generality, we assume A0 is not 0. But multiplying a real number to a solution is still a solution. So if we want, we can also make A0 to be 1. Okay, so this is why A0 is not 0. So A0 is not 0. To continue our discussion, I copy this computation to the next page, and then we deduce the relations between all the coefficients an. Okay, so I copy this result to the next page, that is here. So because as I said, all the coefficients of the power of xr and xn plus r must be 0. So we have since a0 is not 0, so fr must be 0. Okay, and moreover, the coefficient of xr plus n for n greater than or equal to 1 must also be 0. Therefore, we have this equality. So this equality is called recurrence relation. So we expect to determine the order an from this recurrence relation. But we first need to take a suitable r from this equation, initial equation, to determine the r. So this is an equation of r, a quadratic equation. It has two roots in the complex plane. The two roots can be both complex and or they can, if they are complex, they are a pair of conjugate complex number. Or the fr equal to 0 has real roots. The real roots can be equal or not equal. Okay, so we have several cases to study. So if the fr equal to 0 have complex roots, as I said, these two roots denoted by r plus and r minus, they are a pair of conjugate complex number. So in this case, capital F r plus and plus n and r minus plus n are not 0 for all n. Okay, because the only complex number make capital F to be 0 is r plus and r minus. But for n equal to n greater than for n from 1, 2, 3, and that is all non-negative integer n, r plus and r minus plus n will not equal r plus and r minus. Therefore, this f will not be 0 because f only have two zeros, that is that are r plus and r minus. So we deduce that this is not 0. So in this recurrence relation, we take r equal to r plus. Since the coefficient of an is not 0, and an can be expressed using a0, a1, a2 until an minus 1 using this recurrence equation. Since the coefficient of an is not 0, therefore an equal this summation from 0 to n minus 1 divided by a non-zero number, capital F r plus n. So we can determine all the an, no matter r is r minus or r is r plus. Okay, so and all these an are determined using the a0, an minus 1. Determine all the aj, all the which index before n. So every an can be determined by a0. As I said, we can assume that a0 is 1. So this determines all the an. Therefore, we obtain the two solutions. For the r plus, we have a solution. The corresponding an denoted by an r plus. Similarly, for r equal to r minus, we also has a solution denoted by y minus, where the coefficient of xr of this possibly singular term is r minus, and the corresponding coefficient is a n r minus. Okay, so this is the case that capital F r equal to 0 has complex roots, which are a pair of conjugate complex number. Now, this complex, because r plus and r minus are complex, so this is a complex valued function. But our function is of real coefficients. We want to find real solutions. We don't want to work with complex function. Okay, so by the basic property of linear ordinary differential equation with real coefficients, we know that if we have a complex solution, the real part and the imaginary part of the complex solution are real solutions. So from these two complex valued solutions, y plus and y minus, we can obtain the real part and the imaginary part. This y1 and y2 are real solutions of our equation, and it can be checked that these two solutions are linearly independent. Therefore, they form a fundamental set of solutions. So this completes our discussion of the case that capital F r equal to 0 has a pair of conjugate complex roots r plus and r minus.